Our goal for learning in this video is to be able to sketch logarithmic functions using transformations, and they're the familiar ones A, B, C, D, and please note the equation there for our general logarithmic function. And we might see there's a relationship between log and exponentials. In fact, we've mentioned it before, they're inverses. And being inverses, they're symmetrical about the line y equals x. Inverses do that. And so y equals 2 to the x is an inverse of log of x to base 2. They're both inverses. And if we look at logs 2 and their bases, that originally said that they said log of a half x. That's not what it meant to say. It meant to be log of x to the base half. They also have a certain relationship, and we're going to have a close look at them in this video. So basically, four main shapes. Y equals log of x is the green one. Tracing that now. Remember, ln x, natural log of x, is log of x to base e. Just like we used e of x before, we're going to use that as our basic touchstone, our basic one, because it's a commonly used one. And it shouldn't be any great surprise that negative of log x is mirrored in the x-axis, a bit like negative e to the x was. If we go back to y equals log x, we can see that mirrored in the y-axis is log to the negative x, a bit like e to the x and e to the negative x were mirrored in the y-axis. If we apply both transformations, we get negative log to the negative x. Now, negative log to the negative x does kick up, but it's not the same as an exponential. It's not the same as e to the x. Okay, so they do not equal each other. At first they appear to be the same or similar, but they're not. Log functions have a different asymptote to the exponential functions. Exponential functions have a horizontal asymptote, and logarithmic functions have a vertical asymptote. Alright, so exponential horizontal and log vertical asymptote. It also there's also a difference there with the intercepts between exponentials and logs. Exponentials have a y-intercept and logs have an x-intercept. So exponentials have a y-intercept and logs have an x-intercept. Now, in regards to the asymptote, the vertical asymptote, why does something like log of x, which is the green function plotted above, why does it have an asymptote the y-axis? Why is, as we approach x equal to 0, why does that start to produce that asymptotic effect? Well, the answer lies in log of 0. Log of 0 is undefined. So that's basically saying it doesn't matter what base you use, either it could be base 10 or something else, base 2, you name it. Log to base e of 0, what does that mean? Well, basically you're saying e to the what equals 0. Okay, so if x equals log of 0, or log to base e of 0, rewriting that, in other words, is e to the x equals 0, we can't find a value for that because there's e to the x there in red. It doesn't have such a value. You can approach negative infinity, okay, and it'll just keep getting closer and closer to that x-axis, y equals 0. And so likewise with the log function, the blue one, as we approach log of 0, which is the y-axis there, when x equals 0, it approaches it without even touching it. It just doesn't do it. So there is no suitable value. So keeping in mind the asymptotes is perhaps the easiest way to work out whether we're looking at an exponential or a log function, if in doubt, because with some transformations it is easy to get them confused. Okay, let's consider some examples, and if you were paying attention to the earlier videos on graphing exponential functions, this should resonate. We have in these first few examples here, we're going to use the same steps of thought, and you can see we're going to look at the basic shape, see which basic shape it matches, and use a significant point to see how the curve changes, at least initially, to give us an idea of how abrupt it changes. We're looking at, instead of the horizontal asymptote, we're looking at the vertical asymptote this time. Instead of the Y intercept, we're looking at the X intercept. So more of the same, although it's different with a different function, if that makes sense. Looking at the first example at the top, 2 plus 2 a log of negative x. So it's the type log negative x. So the shape's like this basically. I'm going to use natural logs as we said before. And so if we've got our axes, we're essentially looking at the following. So it doesn't, remember, it will not cut at 0, 0, it'll cut before that, and it'll be asymptotic down that way. Alright, and we can try a significant point if we like at this time. Let's try x equals negative 1, and we sub it in. So we've got y equals 2 plus 2 log of negative 1. 2 plus 0 is 2. So when we've got x equals negative 1, we've got the point 0, x equals negative 1, we've got the y value of positive 2, which might be about there. So we can put that in. And the reasons for choosing that particular number are a bit reminiscent of when we looked at it for exponentials. Looking at a handy value that's easy to sub in, that's easy to calculate, that shows you how a curve rises or falls away from its asymptotes and away from its intercepts. So that is a handy point. So it demonstrates more or less how it rises or falls, and it's easy to calculate, and that's what we said about exponentials when we did the same thing there. The reasoning for asymptotes is slightly different to that than we did with exponentials. We said d was the asymptote. It's certainly not the case with logs. So we look at the function, or even take a peek at the graph, and the function is undefined when x equals 0, because log of 0 is undefined. 2 plus undefined is undefined. So asymptote is the line y x equals 0. So that's the y-axis, in other words. So we've got 2 out of 3 steps done, and looking at the x-intercept now, well, the x-intercept is still when y equals 0. So let's have a look at that. We've got the function, let's set y equals 0. 0 equals 2 plus log of negative x. We do some rearranging. Negative 2 equals 2 log of negative x, and then we rewrite that, we divide by 2 first, I should say, and we can do that on both sides. So we have now negative 1 equals log negative x. Then we can rewrite it in exponential form. Just remember, that's log of base e to the negative x. Alright, so we're saying we have a base of e, so we have e to the negative 1 equals negative x. And rearranging, we get x equals approximately negative 0.37, and so we could mark that on here. Okay. Instead of rounding to, you could just call that point there negative e to the negative 1. That point there, if you want to use exact values, which is nice to do. Okay, you could write that as negative e to the negative 1. It's the exact value, but they're both correct answers. Okay, so moving on to the next one, going a little bit quicker now. So we're looking at the basic shape. The basic shape here will be like y equals log x. And significant point, let's have a look at that. You could take a quick look at the graph of this, and also note that if we have log of 1, that's equal to 0, and that's easy to calculate, so maybe we should make x equal 3. And let's look at the graph. So yeah, that would probably be good. So 3 is there. Interesting enough, x and y seem to have the same coordinates, so let's try that algebraically now. So switching back to our working. So using x equals 3, subbing that in, we get log of 3 minus 2 plus 3 is 0 plus 3, which is 3, so we have the point 33 as our significant point, so we can mark that on. Next step is the vertical asymptote. Using technology to have a look, it looks like the graph is going to be asymptotic as x approaches 2, so that gives us a bit of a heads up that it might be that. Let's also do that algebraically, which is most important. So when x equals 2, we've got y equals log of 2 minus 2 plus 3, which is undefined, plus 3, which is undefined. So it's undefined there. And basically we have to write that the asymptote lies along x equals 2. So we're now looking at the intercept. So just showing a bit of working there for X intercept equals is when y equals 0. So we've got 0 equals subbed in there for the expression for y. Take 3 off both sides, and remember natural log is log to base e, so we've got e to the negative 3 is x minus 2, and then lastly we rearrange and calculate. Can write it as the exact value 2 plus e to the negative 3, or approximately 2.05, and then we can put all those things together and plot our sketch and label them on there. And voila, all those features are on there. Alright people, so we got 1 minus log 4x, and firstly we've got to work out what's the basic shape. It'll be like y equals negative log x. Could be its basic shape. If you rearrange that, it would be negative log 4x plus 1. So you've got the negative a value on the front essentially. So let's consider a significant point which helps us with this. This might be a good time to plot it on your graphics calculator to get a bit of a look at it too, and we can see that we've got that sort of thing, and we've got to show a significant point. Alright, so we've got log 4x equals 1, and so we've got e on 4 equals x. We could just write our answer like that, quarter e, or e on 4, or you could basically approximate that, approximately 0.68, and we mark all those things on there. Now something happens when x equals 0. We've got y equals 1 minus log 4x, and subbing in 0 we've got log of 0, which is undefined. So x equals 0 is the vertical asymptote. And we mark that in as well, and our sketch is complete. In the next video we're going to refine this method and add to it the idea of transformations, and this is what we did with exponentials. So this one's looking at some key points. We're not going to reject them in the next video, but we're going to add also transformations and A, B, C and D for the constants